Now let me handle another problem under flash columns. Now as you can see, you are required to use SRK method for thermophysical properties. Now all the data is given here in this problem, in this figure. Now what is happening is, typically you are admitting feed. Now the flash column is operating at some conditions. Now in the beginning you may be allowing all the liquid as a product, but now you are required to handle three different cases. Suppose if 50% of the liquid product is sent back in the form of a recycle, mixed with the feed, once again sent into the flash column, what will happen to the product, liquid product and vapor product compositions and their vapor fractions? In the same way, if 25% is recycled back, what will happen? And if nothing is recycled back, what will happen? So you are required to do all these three cases and try to compare the compositions of the vapor and the compositions of the liquid along with the vapor fractions. Now let us try to demonstrate this problem. As you can see, the components that are handled are methane, ethane, propane, N-butane, 1-butene, 1,3-butadiene. Right? Once again, we are going to use things like PSI, LB per hour. So we can use English unit system. Now let me go back to Aspen, try to declare all the components that I have: methane, ethane, propane. N-butane. Now till now we have been handling only binary systems. Now in this particular case, you can see whatever calculations that you are doing earlier are more or less going to be similar, even in the case when you are going to handle multi-component system. 1,1-butene, 1,3-butadiene. Yeah, I think we were able to take care of all the components that are being handled in this problem, right? Anyway, it is already mentioned that you are required to use RK-Sauvé, Redlich-Kwong-Sauvé equation of state for estimating the properties. So let me consider this as SRK, Sauvé-Redlich-Kwong equation of state. So having selected the property model, now once again you are required to specify the input, go to simulation environment. Now define the problem. Now again, I may have a flash column. Then, you know, the bottom product is going to be split up into two parts. Part of that probably is going to be recycled. Let me rotate this icon. Rotate right. In the same way, the fresh feed might be getting mixed up with the recycle stream to give rise to the combined feed that may be entering into the flash column. Now, depending on our requirement, we should be able to process all the three cases in this example. Now, let us say this is the fresh feed that is going to enter into the flash column. Now, the combined feed is going to enter into the flash column. Now, the vapor product is going independently. The liquid product is sent into a splitter, and part of this is taken as a product. The remaining part is going back in the form of a recycle. Now, as per the problem statement, you are required to simulate this particular problem for different cases. In fact, you can see now there is a small pressure reducing valve because the pressure of the feed is 100 psia, whereas the flash column is operating at 25 psia. If you want, you can also include this, and the valve will be able to reduce the pressure from 100 psia to 25 psia. Anyway, it may make some difference with respect to energy balance. In fact, let me also introduce that in the problem. Now you can say pressure changes, valve, so include that. Let me make it slightly bigger. Now reconnect destination. Now you can connect the exit from the valve to that of the feed. Now we'll be in a, I think we have taken care of all the details. Now we will have to specify 50, 100, 200, 870. Yeah, let me specify this. Go to the next input screen. So the temperature is 85 degrees centigrade, 100 psia. 85. Now let me change the unit system to English. So 85 degrees Celsius and 100 psia. The flow rate of each of the components are given 50, 100, 700, 870, 700, 870, 1176. And 1,3 butadiene is 5,130. Yeah, we were able to specify stream 1. Go to the next input screen. Now you can see the flash column is operating at 5 degrees centigrade and 25 psia. So 5 Celsius and 25 psia. So vapor liquid, right? Say next. So the information with respect to the block is complete. Now we are talking about the stream splitter. Now the first case I would like to handle as the split fraction with respect to S5. Try to be careful with respect to what you are going to define. If you go to main flow sheet, S5 happen to be the product. So when you are not going to recycle any part of the liquid in the form of recycle, then everything should go into S5. Let me deal with this case first. So the split fraction with respect to S5 should be 1. So obviously nothing will go into S6. Okay, say next. Okay. Flash column, adiabatic flash, outlet pressure should be equal to 25 psia. So it will reduce the pressure from 100 psia to 25 psia. Say next. Now we have completed all the input specifications. Say OK. Now, why all these blocks are being iterated? Now you can see if you want to if you go to the main flow sheet. Now as we said earlier, now in order to compute this block, remember we are going to use sequential module approach. In order to compute this block, we have specified stream 1. But in order to calculate the output from this mixer S2, we need to know S6. But we have not specified any amount for the recycle stream. This stream is not known. So what the simulator does is all the recycle streams are going to be tear streams. It makes assumption with respect to the tear stream, calculates the output, then computes the next block, then evaluates S6, compare it with your previous requirement, previous assumption, and if they match, fine. Otherwise, these blocks once again are going to be iterated. Typically, because the recycle stream is connecting B2, B3, B4 and B1, now all these blocks are going to be iterated till convergence is achieved with respect to the recycle. Now that's what is happening if you look at the control panel. So because of the recycle loop, now all these blocks are iterated 2 times. by the time the recycle has come to a convergent solution. In fact, in this case, there is no recycle at all. But to start with, the simulator doesn't know that nothing is coming from stream 6 until it solves the flash column. So that's why we were able to come to a quick convergence. Now, once again, you can observe the method. Till now, I think we were looking at secant method. Now there is a small change. Another method has been used. Now anyway, we'll go into such details later. Now let us look at the stream summary. Particularly, I am interested in, because you can see nothing is being recycled. S5 happened to be the liquid product. Now let me also introduce in the report the mole fractions. Once again, look at the stream summary. Now you can see the mole fractions of each and every component. Now for convenience, I'd like to put it aside in the form of a report, especially with respect to streams, so that we will be able to compare it with another case. Whatever you saw is available here in the form of a notepad file. Now let us go ahead with solving the other two cases. Now, in case if 50% of the liquid product is recycled, what is going to happen? Now, let us specify that by going into the flash column. Now, earlier, we have given everything should be taken as a product. Now, only 50% is taken as a product, and obviously, the remaining 50% is going back in the form of a recycle. Now, let us evaluate, let us simulate under this particular case and try to see what will happen. You can once again see the report with respect to streams. Select all. Okay. Now, especially I am interested in looking at both the streams. Probably you can take a printout and make a comparison. Now you can see the mole fraction of methane is exactly similar. Ethane also similar. Propane is also similar. This is also similar. Now 0.1458, 0.6392. Now in the same way, we can observe what is the amount of vapor generated. So where is the total moles? Total flow. This was the total number of moles entering into the flash column. Out of that, now your S5, S5, now you will have to compare S5 here. You can see S5 compositions 1.8123, 2.36276, 5.117, 0.1509, 0.6785. And what about the amount, total amount? LB moles per hour is 5075. What about here? 5075. Now, when you are having some kind of a recycle, 50% of that stream S6 now contains some input. Whereas in this particular case, there is no S6. S6 is 0 because we are not recycling any liquid product. Despite recycling some part of the liquid product as recycle, you can see practically there is no change in the product composition as well as the amount of vapor generated. Now, of course, you can once again simulate when you come into the lab, and I would like you to analyze why this is happening, especially in this case. Now, are you going to observe the same result even if you handle this kind of a problem with any other system as well? I would like all the students to analyze and come up with a reasonable answer for this kind of a behavior. Also try to comment whether similar behavior can be expected irrespective of the type of system that you may be handling, irrespective of the conditions at which the flash column may be operating, irrespective of the amount of recycle that you are trying to send back. Now it is for you to ponder over these questions and come up with some kind of a solution, some kind of a valid observation. Thank you.